Hello students, today we'd be talking about the chapter Kinetic Theory of Gases, where we'd be learning about how gases behave in different temperature, different pressure and different volume situations. To start with that, today we're going to study about the theory, and then we would go to some basic problems and then to the advanced problems. So we have Prasoon with us who's going to talk about the assumptions and theories in this particular chapter.
So first we start with ideal gas. What are the assumptions behind the ideal gas?
Okay.
For the ideal gas, the first point we have is that the number of molecules are large and the average separation between those molecules is large, and the molecules, the particular shape or the dimensions of the molecules are very less as compared to the dimensions of the container.
Okay.
The next point is that the molecules of the gas obey Newton's laws of motion. Basically, force equals ma, and the law of inertia, that if it is moving it will keep moving unless acted upon by an external force.
So so these are the formula which is going to apply in these molecules. So they would rebound the same way as it would in classical mechanics.
Yes,
okay.
Like even if they collide with the walls, or even if they collide among themselves, which is exactly like the next point, that any collision with the wall or the molecules are elastic. Elastic to say that the momentum is conserved, and along with that the kinetic energy is also conserved.
Okay.
So basically we can explain it with the help of a diagram here, like if a particular particle is moving towards the wall.
Okay, so this is a particle moving towards the wall.
Yes, with velocity v. And after collision it will come back with a velocity v itself.
So after collision it will come back with velocity v.
Yes, so this is basically the elastic collision which we are talking about.
Okay.
The same happens between two particular molecules also. And force between the molecules are negligible except during collision.
Okay.
So basically if the molecules collide among themselves or they collide with the wall, only during that time the forces act, otherwise there are no, say, intermolecular forces. And
okay. So you're saying that this particle and this particle would not interact in any other way except for the time when they actually collide.
Yes.
Here, in which case Newton's law
would be very near to each other.
Okay.
So basically this also gives us the inference that the potential energy would be zero because there are no intermolecular forces.
Right. Okay. Yeah.
And these gases are pure substances, and all the molecules of a particular gas are identical. There is no as such difference between them.
Okay. Alright.
Now we have a very interesting point here, that the motion of gas molecules is completely random. Random to say that its probability or its ability to move in any particular direction would be the same.
Okay.
So because of this we get a particular distribution in which, like, some molecules are with high speed, some have low speed, and some are very high and some are very low speed, but the distribution, the overall distribution or the fraction of molecules which have a particular speed, that does not change with time.
You mean to say a particle can move either in this direction or z direction,
yes.
And it could be in any direction, we don't know that, so we can only take out the probability of that, but not be sure about
and
it.
That probability would be equal for every particle.
Right. Okay.
Now we see what is pressure. So pressure is the average force exerted by all the gas molecules per unit area on the wall of the container.
Okay. So pressure is equals to force exerted per unit area. Yeah.
This will be the area of the container.
Right. So if you have a container like this, right, and this has to be the area.
This has to be the area.
Yeah.
And the force exerted would be pressure into area.
Okay.
So
sure.
Yeah. Let's just see now what is the work done by the gas.
Okay.
So we draw this particular cylinder again, but with a piston, so that we can tell what the pressure would be and then what the force would be.
Okay. So I'll make a piston. I'll make a cylinder first. Let me just make a cylinder.
Let's make a cylinder.
Yeah. This is our cylinder. Okay.
And this has a piston in it.
This has a piston in it. Let's make it a cylindrical.
Okay, and say the length of this from the bottom of the cylinder is L. The distance of the piston from the bottom is L.
Yeah.
Now the pressure inside would be P, and let's say it moves a particular distance dl.
So here there's a lot of gas which you fill.
yes.
Okay,
The
and it is
pressure
in
of the gas is P.
P pressure. Yeah.
Yeah. So and we assume the area to be A, area of the piston.
This area is A. Okay.
Now say because of this pressure, the gas makes the piston move a particular length dl.
Okay, so because of this pressure, this particular piston moves. Okay, let's just change it to different color. Moves dl distance. So now this is dl. Yeah.
Okay, so now basically we find the work done. The work done as we know it to be is force into the displacement.
So we have to find the work done. Work done is equals to force into displacement. Yeah. Which in this case is force will be pressure into area, right? Yes. Okay, pressure into area. Into distance here is dl. So this is work done. Yeah.
Yeah, this is, and basically for this particular case the work done would be very small because the dl is also very small.
Yeah.
So we denote it by dw.
Okay.
Which is dw equals p into a into dl. Now to find the work done, let's say it moves distance more than dl, a finite distance. We just integrate this. So we integrate integral dw equals integral p a dl.
So we'll now integrate this. So it'll become integral of dw is equals to integral of p a dl.
Now we say that P into P is the pressure. A into dl, as we observe, would be the volume change.
Okay.
Because A was the area and we multiplied with dl, that is the volume that has increased. So we can write this formula as P into dv. Integral
P into
the whole integral of P into dv.
Integral of P into dv. Right.
Now the limits of integration are left, so that would be from the initial volume to the final volume on the right hand side.
Yeah.
From Vi to Vf. And this will give us the work done.
Okay, so this gives us the work done. Right. So in this case, in case the pressure is constant throughout, we could just call it P into integral of dv, but the pressure would also change. It might change because the volume is changing, right?
Yes.
So it'll depend upon how pressure changes according to velocity.
Yes, so
volume
pressure might be a function of volume.
Yeah.
So
right.
So give us the right answer.
Right.
So this formula is basically valid for any shape of the container, and this is valid for a quasi-static process, which is a very slow process in which in almost every step the whole system remains in equilibrium, because during that time only we can define what P means, what T means, and what V means for the gas. And suppose we have to compress the gas, so work done on the gas would be this if the word on is used, or if the work done by the gas is asked, that would be the negative of the work done by the gas.
Okay, so what do we have next?
Here we have the equation of state of ideal gas, which is PV equals nRT. P means the pressure of the gas, V is the volume of the gas, N is the number of moles, R is the universal gas constant, and T is the temperature in Kelvin.
Okay, temperature in Kelvin. Okay.
Now we have it's the temperature in Kelvin. That has to be a capital K, as we denote by Kelvin.
Yeah.
Now the value of R we can have is P is in Pascal, V is in meter cube, basically the SI units. Then R has to be 8.314 joule per Kelvin per mole, and if P is in atmosphere, V is in liter, then R would be 0.08206 liter atmosphere per mole.
Right. So it would help us to remember these values in case P is given in different formats. Okay.
Yes. Now what is temperature? Temperature is a direct measure of the average kinetic energy of the gas. Now how is it that let's see how we can basically relate the temperature with the help of our equation of state of ideal gas to the kinetic energy of gas. So let's say we have a 3D box with dimension d, basically a cube with dimensions d.
Okay, so should I draw cube with dimension d? Okay, so this is
cube with dimension d.
Okay, so this is a
here
cube.
We have a cube which we take our container.
So
to
we'll
which we'll
just
prove a
mark
point.
its dimensions as d. Okay, so this is d, and this is also d. Yeah. Now what
So
should I do next?
now let's say we have a particle whose x component. Here we are to start with. We are considering only a component in one direction, because by the principle that the molecules can have direction, or the probability to move in any direction is equal, we would use that later on to basically see it for the other direction also. So let's say a particle is moving in x direction with vx.
So it's moving in x direction
with velocity
vx. Okay.
And after the collision, it moves again in vx, again with vx in the negative x direction.
Okay, wait. So you're going to make the box inside, and what are we trying to find here? We're trying to find how temperature is somehow related to the kinetic energy of the gas, which means we're taking a particular particle here. Let's just make the particle with pink, and this particular particle is moving in this direction, and it collides with this particular wall. All right,
and then it comes back elastically. Now, because the collisions, as we had said before, would be elastic, so the velocity after coming back would be vx.
Okay, so but then it comes back also in vx, and it goes also in vx. Yeah.
Yes.
Then
now the force that it had exerted on the wall, it would be the change in momentum divided by the time.
Right. Okay. So do I write that force?
Yes, the force.
How about do I write it as force x, Fs?
The force on, we can just write it down as the force.
Okay.
The F equals. So the change in momentum would be 2 into m into vx.
So change in momentum
divided by time.
By delta t. Okay.
Now this equals the change in momentum, because it went in one direction with
vx minus vx is equals to 2 mvx.
Vx, yes.
Yeah. 2 mvx. Yeah.
Divided by delta t. Now we can also find delta t with respect to
actually this v should be small v, otherwise now since we are doing it in kinetic theory of gases, this might be confused with volume. Yeah.
Yes, so
delta t.
So now the particle hits the wall after every delta t equals 2d by vx, because let's say it has hit with velocity, particular velocity, it will go back, cover the entire box, and come back again and hit it.
Yeah.
So basically the distance would be 2d, and the velocity throughout is vx.
Yeah, right.
So basically it hits again with the, after a time, 2d by vx.
Yeah.
So we have the value for delta t equals 2d by vx.
Oh,
we can write that down.
So we have delta t is equals to 2d by vx. Now
we substitute the value of delta t into the force. So which equals,
so this gives us
the value as m fx equals m vx square by d. This is basically the force exerted by the particle, by one particle on the particular phase.
Yeah.
Now say if we have a lot of particles, so for that or say for every particle, the force would be force equals m by d into vx1 square.
So what should I write now?
We have to write the complete force. So the force equals
total force will be equal to
m by d. And in the brackets we do v1x x whole square plus v2x whole square.
But what is v1x and v2x?
v1 and v2 are, v1 is the particular one particle, v2 is the velocity of the second particle.
Right. So the particle 1 will have x and y and z velocities, and similarly particle 2 will have, and so
in the x the v2x.
Right. So we are just taking this particular formula to all the particles.
Yes.
Yeah, and to taking out the total
the
force,
nth
right?
particle, so we can write it down as v nx capital N whole square.
Okay, total number of particles is capital N. Yeah.
Yes.
Yeah.
And we close the brackets, we get the total force here. So we just denote it by, say the total force would be force equals N.
Total force will be
N into capital N, which is the total number of particles, into m by d.
Where did the nm come from?
Yeah, m by d was there previously because m is the mass of one particle, d is the mass of another particle, and we are multiplying it by n, and we will divide the whole Vx squares by n, so that we can represent it by the average of the square velocity.
Okay. Yeah.
So we can
so
write
then
it
we
as
write as Vx square
Yeah.
plus V2x square plus
Yeah.
till Vnx square upon n.
Yeah.
And
This
here
is-
this particular thing we'll call something. What are we going to call
we
it?
denote it by Vx square bar.
Okay, so we call it Nm by d Vx square bar.
Yes. So
Now what
V
does that mean? What is Vx square bar?
Vx square bar is the
So Vx square bar is the mean square
square.
of velocity in the x direction, right?
Yes.
So it's the mean square in the x direction. Yeah. Okay, and this should also be fx total, right? Because it's only in the x
yes.
direction. Yeah.
Now, as we had seen before, that the basically probability to move in any particular direction is equal. So let's say let's denote the total velocity of a particular particle, v square would be equal to vx square plus vy square plus vz square.
So v square will be equal to vx
X
square
square.
plus vy square plus vz square. Yes.
For many particles, it would be like v1 square plus v2 square plus till all the n particles would be equal to their respective sums. That is vx1 square plus vx2 square.
Yeah.
Then till vy1 square, vy2 square, and then for vz1 square plus vz2 square.
Right.
And basically then finally we take this sum, so we would get the v1 square plus v2 square till vn square whole divided by n.
Okay. So what
we
should
can
I
write that down, v1 square plus v2 square till vn square divided by n equals vx1 square plus vx2 square till vxn square vxn whole square divided by n.
Shouldn't
This
this be v1 x square, v2 x square, vn x square? Because that's the notation
yes,
which we took,
okay.
right?
Yeah, we took that
So,
notation, so
yeah,
let's
so
just
we
stick to
should
that.
not mix it up here. We should write v1 x square plus v2 x square plus till vn x square. Yeah.
And we divide the whole by n.
Yeah.
And we write the
Plus-
same for y. That is v1 y plus
y square plus v2 y square plus till vn y square upon n plus z v1 z square v2 z square plus upon n. Right.
So this we get as vx square bar.
So here we can
Basically
write
v
this
square, we can write
as
vx square square bar. Bar represents the average plus vy square bar
vy square bar
plus vz square bar.
vz square bar.
Whole this is equal to v square bar on the which we write on the left.
Oh, okay.
We write that on the left hand side.
V square bar.
Now because the motion is random and the probability of going in x, y or z direction is the same, so we can say on an average on a large number of particles, this vx square and vy square and vz square would be equal to each other.
Okay. Yeah,
So-
because the probability is equal.
Yes.
Right. Okay.
So because of that we can come to the conclusion that vx square bar would be equal to vy square bar would be equal to vz square bar. And this
That's
would
because the probability in all the
Yes.
directions is equal. So putting it right here, we get it as
we get it as v
v square bar is
divided by
equals
equal to
to 3
3 vx square bar.
3 vx square bar. Yeah.
And before that we had found out the kinetic energy in terms of Vx square bar only, in the x only. Now if we substitute the Vx square by V square, let's just do that. So basically substituting the force on the wall.
Force on the wall.
Yes.
Yeah.
The force on the particular wall would be the same as we had given here.
Yeah.
Be n into m into Vx square by d.
So I'll just write it here, force on the wall. So here we're gonna do force x total is equals to what was given?
N into m into Vx square bar divide by d.
Right.
Now instead of Vx square we can substitute V square,
which means n into m into V square bar by 3d.
Yes.
Yeah. Okay.
Okay, now this we have got the total force on the wall.
Total force in the x direction.
In the x direction,
Yeah.
or on the wall which is in the s direction.
Yeah, right. Absolutely. Because y direction and z direction won't apply any force on the wall in that particular direction. All right.
Because they are
So this is the total force which we're getting on that particular wall. It's just not in x direction. That's the total force because it's only in the x direction, right? So yeah. Yes.
Now we can write down the pressure with the help of this because it was the average force per unit area.
Absolutely. So pressure would be Fxt upon d square.
Upon d square.
D square is equals to n m
by 3.
Oh, okay. It was actually v square. I just wrote it here. So sorry, that was wrong.
Okay.
That has to go off. Yeah. So that should be v square, and similarly here v square bar upon 3
d cube.
Right.
Now see, we have got d cube, which is the volume of the cube. So we can just write it down as V, or capital V, which is the volume. So this basically equals nm V square bar divided by 3V
cube. Oh, sorry,
3V.
Yeah.
V is the volume,
right,
which is equal to d cube. Now these relations are derived for particle in a cube, but they are true in
this
general.
is velocity and this is volume. So again, I should keep it in a different format. Yeah.
Yes. Now.
Yes.
We can get like PV equals n by 3 into mass of particle into V square average. So this is basically we have derived for a cube, but they are true in general for every type of container for an ideal gas. So
that's another formula which we got.
Yes, we can write that down as PV equals 2 by 3.
So P,
PV equals 2 by 3
equals to 2 by 3
into n, capital N, which is the number of particles, whole into half, whole into half into m, which is the mass of a particle, into V square.
V square bar. Yeah.
Yes. So basically we introduced a half here, and as we can see by now, this half m V bar square, this is giving us the sum or the average of the total kinetic energy.
Right.
So this is how we see that how the pressure.
Right. So what should I write? Then how is it related? PV is equals to 2 by 3 n KE. Should I write KE here?
KE average.
KE average. Right.
KE average of all the molecules.
Right. So this is how it is related to kinetic energy.
So like still now we cannot actually see, but if
the
we
correlation with temperature.
Yes.
Yeah.
But if we replace PV by nRT, n was the number of moles, then we can like exactly see that the temperature is directly related to the kinetic energy.
Is equals to nRT, which is equals to PV, and now we can see that temperature is related to kinetic energy. Brilliant.
Yes.
Okay.